Okay, I'm gonna wait another minute or so. Just wait for a few more people. I'm still missing several people. Hey, Abby. Good morning. Welcome back. Oh, thanks. Good morning. I'm doing well. It's Friday. Sun's out. It's gonna be a nice weekend. And next week it's gonna be like 78 degrees on Wednesday, so I'm like pumped about that. Thanks for asking. Hi, Jennifer. Good morning. Yeah, I guess it's definitely. All right, good morning. Welcome back. I hope you guys are doing well, staying safe, and ready for the best class of the day. Happy Friday. I'm looking for a few people today. I'm looking for Victoria, Edvin, Joseph, Matthew, Nyla's here. Oh, sorry. Sabina, Amaya, Gianna, and Karen. If you're here, please let me know. So any of you guys, if you're not here, obviously you can't say anything, but if you're here, please let me know. Victoria, Edvin, Joseph, Matthew, Sabina, Amaya, Gianna, and Karen. Please throw your name in the chat or unmute. All right, let's get rolling. So a couple announcements. If you're a junior or senior and you're interested in going into the prom, please check your grade level Google Classroom, and there's a survey or something on there regarding prom. If you're a 10th grader and you want to return back to Proctor first time in over a year, you have the ability to on Monday, May 3rd. So Monday, May 3rd, I'm guessing there'll be something sent home to you guys so you guys can figure out what you're doing. If you're coming back remote, coming back full time. So that's going to be obviously sent back to you somehow. Sure. It'll be the same routine as I talked about. You have to wear a mask, we'll social distance. Right now in class, there's only 2 people in class. There are a handful of 10th graders in here. So if a lot of 10th graders come to school, then we'll definitely spread out in the classroom. The routine in my class is going to be very similar to what we're doing now. I'm not going to forget about the people that are home. Virtually learning, I'm not going to penalize you. I'm not going to forget about you guys. It'll be very similar to what we're doing now for the routine. If you have any questions on the return, please ask me now because I do have a department meeting later today. I'll have a meeting today. I can ask any questions that you may have. Or you could ask a junior or senior that's attending and see if they like it. What else? Any questions for me? That's a new one. Yep. All right, moving on. Let's figure out what's going on for the best class of the day. Here we go. Welcome back. Happy Friday. Quote of the week comes from an unknown source. Good things come to those who wait, but better things come from those who work for it. If you're willing to work hard in life, you could do anything you want. Today's Friday, April 23rd, 2021. Today's a day 2. We are on a new unit, acid, bases, and salts. We're going through topic number 1, inside and out. We're going through Arrhenius acids, Arrhenius bases, and some basic properties for acids and bases. We'll start off with a crash course video on acid and bases. We'll jump into the guided notes. We'll watch another YouTube flick. We'll analyze some examples, and then at the end of class, there should be like 15, maybe 20 minutes left for you to work on the exit pass, which is due tomorrow. So that will be due tomorrow. The exit pass didn't save the way I wanted it to. The exit pass is due tomorrow on Arrhenius acid bases. So is topic number 5, exit pass, due tomorrow as well. Additionally, your guided notes should be completed for unit number 8. You should have all your notes for unit number 8 completed, your pictures completed. If you drew a voltaic cell on hand by hand, that should be uploaded and submitted by tomorrow. 3 things due tomorrow. Guided notes for unit number 8. Topic number 5, exit pass, electrolytic cells. And exit pass, topic number 1, acids, bases. 3 things due for tomorrow. This week, 3 things due. All right, so that's the agenda for today. Below, you can see the attachments. We have the reference table. You have the little YouTube flick, second YouTube flick. As I play this video, maybe you want to open up your guided notes to start getting prepared for today's class. For one more person today. Oh, Isaiah Clark's here. Should I let him in? See ya. I don't know who Isaiah Clark is. All right, here we go. Crash course video on acids and bases. Acids and bases, they're all around us. Go outside, go to the Adirondacks. Acids and bases are all around us. It's definitely a hot topic. Here we go. Acid-base solutions.
All right, so you're studying chemistry. What's the worst that can happen? In most classes, the worst that can happen is just abject total failure. Just like failing a test, failing the class, having to rethink your life choices, maybe even quit, drop out of school, get a job at a diner, and start smoking Lucky Strikes. But in chemistry, the worst thing that can happen is death. And I don't want to make light of this. Labs are dangerous places. Chemists die younger than the average person, both because of workplace accidents and cancer caused by exposure to chemicals. But chemists have also done more to increase the average lifespan of humans on Earth than, in my opinion, any other profession. So it's a necessary hazard. Last week we talked about stuff mixing together, and that's important for sure, but today and for the next few weeks, we're going to talk about the actual reactions happening in those atoms reorganizing themselves to create whole new substances that make our know and love. Some of them are benign and beautiful, face-meltingly terrifying. And that's not hyperbole, I mean actual melted faces. Captain John Mullen, there. He blazed the first wagon trail across the Rocky Mountains into the interior of the Pacific Northwest. The captain's only been standing in this spot right here for about 75 years. And look what's happened to his face. I know this maybe isn't the face melting you were expecting, but we're not so gruesome here at Crash Course Chemistry. The sorry state of Mr. Mullen's face here is the result of an acid-base reaction, one of the 3 major types of reactions that happen in solution that we'll be talking about here at Crash Course Chemistry. And the acid that did this was mostly sulfuric acid. I may be wondering who's been coming by and throwing sulfuric acid on statues. Well, actually, what's been doing the throwing is clouds, the sky, though the actual source of the sulfuric acid, that's 400 miles away at the Colstrip power plant in Colstrip, Montana, and also at coal-fired power plants all over the United States. The United States of America burns about 1 billion tons of coal per year, and most of that coal is mined right here in the U.S. Montana, where I live, is home to the Powder River Basin, a geographical location responsible for 40% of America's coal output. Between 50 and 70 freight trains ship out of the Powder River Basin every day. Each train has at least 115 coal cars and is more than 1.5 miles long. And all of this coal burning, it has effects, significant effects, acidic effects. But first, what exactly are acids and bases? Well, acids, Sour. So sour. That's the first thing that we learned about acids, actually, and that's why acid actually means sour in Greek or Latin. Latin. And acids are excellent at dissolving stuff. They kill things and melt your face. What about bases? You might have some idea of what a base is. Bitter tasting, slippery, like soap. Soap is, in fact, a base. And bases, like acids, are totally dangerous and can melt off your face. They're also like the anti-acid, basically. In fact, they're in antacids. If you mix acids and bases together, they neutralize each other. But as with most things in chemistry and in life, when it comes right down to trying to define exactly what something is, it gets weird and messy and confusing and terrible. So, forget everything you ever learned about acids. Wipe the slate clean. The most common acid on Earth is water. What? And water is also the most common base. And am I saying this purely to confuse you? Yes! Well, mostly to convince you that the world is way more complicated than you thought it was. In 1923, two guys simultaneously defined acids and bases in the exact same way. Bronsted and Lowry defined them. They didn't classify them by how they acted or what they tasted like or even what they were made of. They defined them. And this was an impressive feat because a huge class of molecules, to some extent or another, act as acids and bases. So to come up with a definition that fit all of them, that was not so simple. Bronsted and Lowry defined an acid as being anything that donates a proton and a base as being anything that accepts a proton. And when we say proton, what we're talking about here is a hydrogen atom without its electron. Usually this is happening in water. Acids and bases can react in a gas, but almost always they're in an aqueous solution. And when a proton gets donated in water, it is accepted by water, and H2O is converted into H3O+, the hydronium ion. So when an acid is added to water, it dissociates, like any other ionic compound, forming H3O+ and a negative ion. The acid has donated a proton to the water. Also, a little chemistry terminology thing, we usually just write H+ or say protons in solution, when in fact we are referring to hydronium ions. It's just a shorthand. In reality, H+ in aqueous solution is always H3O+. Let's take a look at the dissociation of hydrochloric acid for some more terminology bits here. You see right off the bat that the HCl is donating a proton, but with many acids, particularly weaker acids, the reaction can actually go back the other way, with H3O+ donating its proton. So in this situation, every chemical in the reaction, also sometimes called the major species, can be called an acid or a base. On the left-hand side, the water is accepting the proton, so it's the base, and HCl is donating it, so it's the acid. And on the left-hand side, the Cl- would be accepting the proton, so that would be the conjugate base, and the hydronium ion is the conjugate acid. The phrase conjugate acid always used to confuse me because I thought it had something to do with conjugating verbs, but it's actually the older original sense of the word, the one where conjugal or marriage-related visits for prisoners come from, which means joined together. For every acid, there is a conjugate base, and for every base, there is a conjugate acid. Previous definitions of acids and bases, particularly the one proposed by our old friend Arrhenius, relied on specific major species, most notably our friend the OH, or hydroxide ion, and while hydroxide is in most bases, it's not in all of them. For example, ammonia acts as a base when it reacts with hydrochloric acid to form ammonium chloride. There's no hydroxide, but there's definitely proton donation and acceptance going on. Now, acids and bases are not all created equal. Certain acids really like to get rid of their protons and will only reluctantly convert back from their conjugate base by accepting the proton. We call them strong acids, and the conjugate base is a weak base. The same can be said for strong bases and their weak conjugate acids. The reason why all of the most interesting acid-base chemistry happens in water is that dihydrogen oxide is really great at being either a base accepting a proton from an acid or an acid donating a proton to a base. Thus, water is the world's most common acid and also the most common base. So, what does any of this have to do with power plants and John Mullen's face? When coal is burned, the sulfur in it reacts with oxygen to form sulfur dioxide. That sulfur dioxide then reacts with water and oxygen in the air to acid. Damages limestone and metal and acidifies the water supply, making life harder for fish, coral, salamanders, and pretty much everything else. Limestone is mostly made of a chemical called calcium carbonate. The carbonate acts as the base, accepting sulfuric acid's protons and converting into carbonic acid, the conjugate acid, which breaks down into CO2 and water. Calcium and sulfate ions may precipitate as a salt that's more commonly known as gypsum. Okay. So the average ton of coal burned in America is about 3% sulfur. Supposing 100% of those 30 kilograms of sulfur leaves the smokestack and converts to sulfuric acid, how much limestone could that completely wash away? As I've said before, just follow the units. 30 kilograms of sulfur multiplied by 1,000 grams per kilogram, multiply that by 1 mole over 32.1 grams of sulfur to get 935 moles of sulfur in every ton of coal burnt. Now, if every mole of that sulfur is converted to H2SO4 and every mole of that sulfuric acid reacts with a mole of limestone, converting it to a mole of gypsum, then that's 935 moles of limestone dissolved. There are 100.1 grams of calcium carbonate per mole. If we multiply that by 935 moles, we get 93,600 grams, or 93.6 kilograms. So each ton of coal burnt by a U.S. power plant produces enough sulfuric acid to dissolve about 94 kilograms of limestone. And as we burn about 1 billion tons of coal per year, it's safe to say that no statue is safe, except for ones built of materials immune to acid, particularly oxidized copper, which will last pretty much forever. Hence Lady Liberty's hand presiding over the Planet of the Apes. So, this is clearly a problem. I mean, not just for statues, but acid rain has killed or harmed huge swaths of forests. At the peak of acid rain problems in the US, the highest recorded acidity was around that of lemon juice, which I can tell you is pretty acidic, high enough to irritate human skin. This first became an issue for power generation when the British House of Lords in 1929 ruled that a power station was liable to damages caused to nearby crops by acid rain. So something had to be done. But what? Well, we already know one very common chemical that reacts easily with sulfuric acid. Good old limestone. And in England, there is lots of limestone. By passing the smokestack gases through a limestone slurry, the SO2 converts to an acid and then reacts with the limestone, forming CaSO3, calcium sulfate. Now we're going to do something a little different for those of you who want to go the extra mile. Assuming that 1 billion metric tons of 3% sulfur coal is burnt in America every year, and all of it is converted to SO2, how many tons of limestone would we need to scrub out 100% of that sulfur? Answers down below in the comments. The limestone scrubber is a good system, but it's not perfect. Many other flue gas desulfurization systems have been developed, and now through a combination of good policy, good science, and hard work, about 95% of sulfur produced in coal-fired power plants in the US is removed before it leaves the smokestack. And through some even smarter chemistry, some of that SO2 is actually converted to industrially useful chemicals, for example, pure sulfuric acid, which is used in paper mills, iron and steel making, industrial cleaners, and chemical synthesis. Chemistry! Causing problems, but also fixing them. Thank you for watching this episode of Crash Course Chemistry. If you were paying attention, you may have learned.
All right, it's a pretty cool video for acids and bases. I really do think it is. So it did talk about a couple different theories for acid and bases. Today we're going to go through a few more, or at least one theory for acid and bases. Before I do that, I do want to just highlight America. I want to talk about acids and bases and how they affect basically the Adirondacks. So anyways, let me do my blackboard here. We have a picture of United States of America. Kind of. So this is my representation, my quick zoom annotate version of the United States of America. Anyways, in the United States of America, what do we have? We are located, we'll say we're located right here in Utica. There's the heart of New York. Right there. And what happens? What else do we have in America? We have some major cities that are around the Great Lakes. So Great Lakes location, we know there's Great Lakes here. Big water bodies. Big bodies of water. Niagara Falls, all that stuff. Let's just think of New York State for a second. If you jump on the New York State Thruway, which there's no like toll booth workers anymore. This is New York State. Let me draw New York State quick version of New York State. Don't color. Right. Roughly New York State. Whoops. All right, so if you jump on New York State Thruway, you should definitely be aware of the geography of New York State. You should know all the way to the west of New York State is a big city called Buffalo. To north of Buffalo is Niagara Falls. You should know that Rochester's next. You should know Syracuse is the first major city to the west of Utica. There's Utica, and then Albany, you should definitely know is there. And then New York City is going to be roughly there. So again, Utica, Syracuse, Rochester, Niagara Falls, Utica, Albany, New York City. If you jump on the New York State Thruway in North Utica, you should know, are you going east? Are you going west? North, south, east, west. If you want to go to Buffalo, Rochester, Syracuse, you're going west. You want to go to Albany, New York City, you're going to have to go east. But anyways, what other major cities are outlining on the Great Lakes? What other cities are going to be on the Great Lakes? Let's think about that for a second. Maybe you have to think of some teams that you know. Think of the states that are by there. What other cities are there? We've got Cleveland, Ohio, Chicago, Illinois, Michigan. It's okay. It's okay, thanks. Michigan's up there. Green Bay, not a huge city, but it's up there. Erie, Pennsylvania. Pittsburgh, Pennsylvania. Okay. Gonna be over there. There is a lot of big cities around water bodies. So when development happened, when development of cities happened, they were looking for water to develop, and they boomed as a city. When those cities formed, all these major cities formed around the Great Lakes. Check out a map next time. Just scroll around like the Great Lakes and see how the major cities are there. When those cities formed, they produce a lot of things. They produce a lot of manufacturing. So manufacturing, Detroit, Michigan, yeah. You know, Ford plants up there. So a lot of these cities have manufacturing plants that produced a lot of waste. So I'm trying to tell you that there's a lot of waste giving off at these cities. If you look at the location, they're about the same location, longitude as Utica is. So what happens? As these smoke plants, they give off some fumes, they're making new things. They're going to go up in the atmosphere. And they're not just going to go straight up in the atmosphere and disappear. What's going to happen is weather's going to take place. Weather's going to take a play here. When weather comes in, they're called westerly winds. When these westerly winds play into our effect, the winds are coming from the west, and they're going to work all the way through and follow the pattern from west to east. These westerly winds are going to take whatever smoke is given off here, whatever chemicals are put in the air, and then what's going to happen as these westerly winds come on over, it's going to pick up some moisture from the Great Lakes, lake effect snow, and then it's going to deposit all that waste, that moisture, onto upstate New York. So it's going to rain in some form or snow in some form in our area. What happens here? It's picking up a lot of acids. So as these westerly winds pass through, it's picking up the acids that are given off from the plants, and then it's depositing a lot of it actually in upstate New York or the Adirondack Mountains. So why is this a problem? In upstate New York, we have the Adirondack Mountains, beautiful range, not too far from here. Think of Old Forge, think of Lake Placid, Lake George. Those Adirondack Mountains, there's a lot of vegetation there. There's a lot of pine trees up there. So with that, there's also these beautiful lakes. And in those beautiful lakes are a lot of things living. So we have the lakes up there in the Adirondack Mountains, some fish just hanging out there. A lot of you guys go fishing, boating, whatever it is up there. Maybe go camping. And what happens to the wildlife up here? It deposits a lot of the acid. So when the westerly winds pass on through, as it rains, what happens? Some acids fall. The form of acids fall into lakes. They fall into the streams. Hello. One moment, please, folks. Thank you. All right, so anyways, as the westerly winds pass on through, they're picking up the acids from the smokestacks from the major cities, and then it's depositing into our atmosphere, our environment. That's a problem because too much acid in the water is going to kill these little fish there. You're going to eat these fish. There's not going to be fish anymore. The water's too acidic. That's going to really mess with them things over there. So think about that process. Next time you go to the Adirondack Mountains, another thing. If you fish in the Adirondack Mountains, thank you so much. Love those. If you go to the Adirondack Mountains and you fish, did you ever pick up a worm or try to dig up a worm in the Adirondack Mountains? Maybe you did, maybe you didn't. You will not find an earthworm in the Adirondack Mountains. Why? The soil is not rich enough for a worm to survive. Thank you so much. So, oh, perfect. So there you go. A little intro on acids and bases. Let's figure out more information on this topic. Any questions for me? That's my little diagram for today. Drawing with Mr. Brown. There we go. So here we go. Acids and bases. Please open up your guided notes. Guided notes. Period 3, period 4. And we didn't get too far into this last time. So last time we just talked about basic properties for acids and bases. Today we're going to jump into that a lot further detail. So acid-base properties, we'll talk about Arrhenius acids today. Topic number 1. So what's going to happen in this unit? We have 3 different theories for acids and bases. We have Arrhenius, we have Bronsted-Lowry, we have Lewis. So 3 different ideas for what an acid is and what a base is. And then we'll talk about the pH scale, we'll talk about indicators, we'll talk about neutralization and titration, which is there. This unit will go by pretty quickly. Hope you're ready. We talked about properties for acid, we talked about properties for bases, and that's where we left off. So if somebody said in my last period the blue's tough to see, I will definitely use a different blue. So you know acids are going to be sour. We know bases are going to be bitter. But we're not going to test, we're not going to sample these samples. We're not going to taste them. You don't want to taste them. Taste them could cause your life, just like that video. You're not going to want to eat a base. You're not going to want to eat acid. Chem lab, we're not tasting anything. College lab, you're not tasting anything. I'm definitely not promoting it. All right, so bases taste bitter. They feel slippery, and they will change the color of an acid-base indicator. They will change the color of an acid-base indicator. Bases taste bitter, they feel slippery, and they're going to change the color of an acid-base indicator. And last but not least, they can be strong or weak. Strong or weak, depending on how concentrated it is. How many of those particles would dissolve? They could be strong or weak electrolytes in an aqueous solution. Strong or weak. Very basic information on acids and bases. Let's go a little further in detail. Let's figure out what Arrhenius acids and bases are. So next up, I'm actually going to put this little section on another piece of paper. Just press enter a few times. Spread them out. Next up, Arrhenius acids and bases. All right, Arrhenius acids and bases. Arrhenius said, a chemist, he studied acids and bases, and he came up with the idea that an acid is going to be a hydrogen ion. Acids, property. Acids typically are going to be red. They will be red. And they're going to contain a hydrogen positive ion, H plus ion. H plus ion is called hydronium, and put that in parentheses. And we will see where hydronium is on the reference table. H plus or hydronium to yield hydrogen, H. Hydrogen ions or H plus. Or hydronium ions in its aqueous solution. Again, we'll figure out what that stuff is real soon. He also said that the bases, base properties, bases are blue, bases are compounds that ionize to yield hydroxide ions or OH negative ions. OH negative is hydroxide. That's a polyatomic ion. You can find that on page 2 of the reference table. Hydroxide, hydroxide, hydroxide. Really, what makes an acid an acid for Arrhenius? Arrhenius acids are H plus or hydronium. Arrhenius bases are OH negative. Common acids, common bases. We'll start off analyzing acids first. Common acids. If we check out table K of the reference table, we will find some common acids listed. New portion of the reference table that we have not analyzed. It's actually on the reference table. Let me zoom on this for a second. So page 1, we already went through all the info there. Page 2, we went through all the information there. Haven't analyzed the reference table in a while. Let's continue on with this. So page 1, we went through everything. April 23rd, we're done with everything on page 1. Page 2, we went through everything. We talked about polyatomic ions. We talked about aqueous solutions. But since I'm on this table, I want to show you one thing. I want to show you a couple of things, actually. Hydronium. If you have a hard copy of your reference table, I would mark this up. Hydronium is an acid. Acid. I'd mark that on the reference table. If you're in front of me now, I'd say take out your reference table, go to page 2, mark up hydronium, and I would say mark up hydroxide. They are given to you. So acid and base. It is given to you. Arrhenius acid, Arrhenius base. Given to you. All right, so anyways, we saw page 2 of the reference table. We saw page 3 of the reference table. We're done with that. We saw page 4. We're done with it. Page 5. We actually analyzed that page already. Very good pace, folks. Page 6, though, there's some stuff on here we did not analyze. Nothing on here we know yet, but today we will understand some of it. So page 6, we'll go through common acids, common bases, and indicators this unit. The last unit will go through radioisotopes. So that we still have to cover. We still have to cover some of these symbols used for nuclear chemistry. We have to cover table P, table Q, that's next unit, and table R, which is next unit. So yes, there is still some stuff that we need to discover, figure out. We went through the reference table. We went through properties of elements. We went through the formulas, everything besides that one right there. And we will do that this unit, titration. But anyways, please go to common acids, table K. And we're going to copy table K right into our notes, common acids. So common acids, HCl. So common acids, we're copying this right into our notes. You guys could do this, you probably already did it. That's such a peaceful bell here. HCl, what's HCl? It's going to be hydrochloric acid. Hydrochloric acid is H and a Cl. Hydrochloric acid. Next up, nitrous acid is going to be HNO2. HNO2. Aqueous. These are all actually aqueous solutions. HNO2. HNO3. Aqueous. I put that in there. You don't need to. Its aqueous solution is nitric acid. Nitric acid. Sulfurous acid, H2SO3. Again, that's aqueous. H2SO4, sulfuric acid. Probably heard of some of these before. Sulfuric acid. Phosphoric acid, H3PO4. Phosphoric acid, H3PO4. Next one, carbonic acid. Maybe heard of that before. That's the stuff in like your beverages, like sodas. Anything that's carbonated. It's going to have carbonic acid. What's the carbonic acid do? It makes the fizzing. It gives it the bubbling texture in the soda. Or it also gives it, like when you buy a can of Pepsi or Coke or a bottle of Pepsi or Coke, when you press it, it's pretty firm. Before you open it, it should be pretty firm. Why is that? That's for like storage, so it doesn't like fall apart, holds its consistency. When you open it, it's gonna go tss. Open it up, it's gonna go tss. Some of the carbonation is gonna work its way up from the liquid all the way through the top to the gas and escape. Your water bottles. Next time you get a water bottle, you open up the water bottle, and if it goes a little, there's a little bit of carbonic acid in there. People always have a fit about why is my water fizz? Why does my water make that noise when you open it? Because when you buy that water, if it's not really firm, then it's gonna make a mess for storage. Or when you buy it, you don't want to buy a water bottle that you just crim together and it's like, ooh, very flimsy. You want it to be nice and firm. You want to grab that bottle, it's nice and firm. You open it, then it becomes a little bit more flexible. Especially like the bigger things of water, like 30-pack of bottles from Walmart or something. You want those to be firm enough. The last one, ethanoic acid or acetic acid. Ethanoic acid formula is going to be CH3, COOH, aqueous. Or it could be acetic acid, which is HC2, H3, O2. So all I did is copied what's in the reference table, put in my notes just to make it complete. So you should know where their common acids are. Common acids, it's on the reference table, table K. Common acids, boom. Easy. Let's look at a common characteristic between common acids. Common acids, what's common between them? Look at the formulas. HCl, HNO3, HNO2, H2SO3, H2, H. Acids are going to have the H within the compounds. Notice that the H is the first thing listed in most of these compounds, the formulas. H is listed first. The charge on H is going to be positive. Acids have an H positive ion. H positive ion. It's going to be positive. H positive. H positive. H positive. The first element is positive. The second one is negative. Yes, you could assign oxidation numbers for this. H positive 1, Cl negative 1. This is positive something, negative somewhere there. Positive, positive. H's for an acid are going to be positively charged. Arrhenius acids. With Arrhenius acids, there's different types of acids. There's monoprotic acid. Monoprotic. Monoprotic acid. Mono in biology class. Mono in science class refers to one thing. Mono, one. Homo, one. Mono, one. Acids that contain one ionizable hydrogen. There's only one hydrogen that can be separated. One ionizable ion. There's only one ion that can be separated in the compound. Monoprotic acid, mono means one, such as HNO3. HNO3 has one H. You see that there. One H can be separated. HNO3, the example is going to be nitric acid. Nitric acid. Mono refers to one. Next one's called diprotic. Diprotic, diatomic molecules. Diatomic means two things. So diprotic acid is referring that two H's can be separated. There's two H's. There's two ionizable hydrogens. Example, sulfuric acid. Sulfuric acid, H2. H2, SO4. Sulfuric acid, there's two H's that can be separated. And last one, you rode on a tricycle when you were a kid. Tricycle had two wheels. Triprotic. Triprotic acid is referring to three different H's that can be separated. Tri is three. There's three ionizable H's. For example, H3PO4, phosphoric acid. H3PO4, phosphoric acid. Phosphoric acid, boom. That's an example. There's three H's that can be separated. H3. No, not all compounds that contain hydrogen are going to be acids. So just because something has H in it does not mean it's going to be an acid. Good thing to be aware of. H plus does not mean it's always going to be an acid. KCl or H. Nope. H2O, not always going to be an acid. You think of it as neutral. All right, Arrhenius acid. So the monoditride, do we have to know that? It's good to be aware of. I will not test you anything on mono, di, and triprotic acids. Arrhenius acids. Only the hydrogen in this Arrhenius acid, only the hydrogen in a very, whoops, I think it was there. In a very polar bond are ionizable. So in a polar bond, polar is going to be two nonmetals sharing electrons. Polar means someone's being a hog and stealing those electrons. Someone has a pull for the electrons. Only hydrogen in a very polar bond are going to be ionizable. So hydrogens are going to be ionizable, meaning you can separate them in a polar bond. Think of an ion. Ion's going to be positive or negative because it either lost or gained electron. Ionizable means how easy it's going to be separated. In such bond, hydrogen is joined together, joined to a very electronegative element. Highly electronegative element. Electronegativity is the attraction for electrons. Which elements are the greatest attraction for electrons? Group number 17. Or F, fluorine has the highest electronegativity. In such bonds, hydrogen is joined, are joined. Let me change it to R, bothers me. Are joined to a very electronegative element. In this situation, when a compound contains such bonds, it dissolves in water. It releases hydrogen ions, releases hydrogen, ions, because the hydrogens are stable. What ions want to do? It's what elements want to do. When they bond, they want to be stable. You want to be stable. You don't want a chaotic relationship. You want something that's stable. Same thing your job. You want your job to be nice and stable. You want to know where you're getting yourself into each and every day of your job. If you have chaos every day, things get crazy. For example, hydrochloric acid is actually an aqueous solution of hydrogen chloride. And the example I'm going to have here, I'm going to scroll them down. I'm going to press enter a couple times so it's on the next page. Hydrogen ion forms a hydronium ion, making the compound an acid. So in this text box here, I'm going to show you the chemical formula for this equation. Hydrochloric acid, HCl. Starting off with HCl, I'm going to blow this up a little bit. It's going to be a chemical equation here. HCl plus water, H2O. Oh, come on. Hydrochloric acid plus water at equilibrium. I'm looking for the equilibrium symbol. I'm going to insert symbol, special characteristics. I'm going to draw the equilibrium sign over here to the right. Remember that symbol? Equilibrium, I don't care which one you use. Or if you wanted to memorize it, it's U plus 21C4. Wow. That's pretty crazy. U plus 21CC. I guess I'll play with that later, figure that out later. All right, at equilibrium yields H3O, H3O positive, plus Cl negative. That is the chemical equation that's described above. Hydrochloric acid breaks down to hydrogen chloride. Chloride dissociates, the hydronium dissociates as well. All that is referring to Arrhenius acids. Bases. Arrhenius base. The most common base that you probably know of is going to be NaOH. It's sodium hydroxide. Sodium hydroxide. It is a cleaning agent. If you go in your chemical cupboard of your house, or if you go to Walmart, look at the soap aisle, the cleaning aisle at Walmart, you'll see a lot of chemicals that make up or have sodium hydroxide in there. Sodium hydroxide is a cleaning agent. After college, I worked at the brewery as a chemist, and we had to test things all the time. We had to test the product every time it moved. We had to test to see whether a tank was clean or not. And when they cleaned a tank, they were trying to get rid of the bacteria or anything that was formed or developed in the tank. So they cleaned the tank. They actually used a solution of sodium hydroxide and water that killed like the bacteria, anything growing in the tank. After they cleaned it, they sprayed it with the sodium hydroxide solution. They then diluted it, neutralized it with water. They did that several times to make sure it was clean. It was a fun job. Sodium hydroxide is known as lye. If you guys make soap at home, I know a lot of farmers market soap's pretty popular now. If you make soap at home, you're definitely using sodium hydroxide. That's going to be an ionic solid. The sodium hydroxide dissociates the sodium ions and hydroxide ions in an aqueous solution. The chemical reaction for this is going to be sodium hydroxide, NaOH, NaOH, starts off as a solid, and then you're going to dissociate, separate it into different ions. What happens? The Na is going to separate. We know the charge of Na is going to be positive, positive 1. You mix it with water, so therefore it's going to be aqueous. And then separating again is the OH negative ions. Aqueous. Kind of like table salt. When table salt dissolves in water, it's very similar to this process. We analyze that. Sodium chloride or bases, because of its extremely caustic nature, caustic means it can do damage to your skin. It's going to do damage to a product. Very caustic. It's very corrosive. Sodium hydroxide is a major component of consumer products used to clean agents. So it's probably not something you think about, like the food plants or beverage plants in the area. They're going to be using some sort of caustic material in order to kill bacteria. So maybe it's Chobani plant. Maybe it's FX Matt Brewery where they make the soda, Shirley Temples. They're using this caustic material to sanitize, to kill the bacteria, to make sure no bacteria is going to be growing in the product. Maybe it's a farm. Maybe you know someone that owns a farm or lives on a farm. They're using sodium hydroxide all the time to kill bacteria. Common bases. Check out table L. We'll find common bases. There's not as many of bases as there's acids. But please copy, record, copy, paste the name and the formula for that section. So please open the reference table. Please find them. Common bases, same page. Scroll on down a little further the reference table, you'll find them. So common bases, first one is NaOH, sodium hydroxide. Nice. You're fast. Sodium hydroxide. Potassium hydroxide is going to be K. Potassium. Hydroxide is OH. Charge is minus, but I'm not going to put the charge here. It's an aqueous solution. CaOH is calcium hydroxide. Base. I think you're finding the common characteristic of a base. Hopefully you see it. And last one, aqueous ammonia, NH3. Aqueous. It's only one on the table that does not have hydroxide in it. Okay, last portion of Arrhenius bases. So last section of notes, I want to finish this portion up right there. Arrhenius bases. Sodium hydroxide, potassium hydroxide are very soluble in water. So bases are very soluble in water. Sodium hydroxide and potassium hydroxide are very soluble in water. What does that mean? They're going to dissolve very quickly in water. Bases are soluble in water. If I take a base and mix it with water, it's going to dissolve. Sodium hydroxide, potassium hydroxide are very soluble in water. Bases are soluble in water. The concentration solution of these compounds can be easily prepared, readily prepared. Such solutions, like other basic solutions, would have a bitter taste and slippery feel. But please do not, when you get to the chemistry lab, do not taste the materials. It's a big no-no. They're extremely caustic. Bases, extremely caustic. And can give you a chemical burn. So could give you a chemical burn to the skin. And can cause a deep, painful, slow healing wound. When you use strong acids, strong bases in chem lab, you'll probably use some chemical resistant gloves just to protect you from an extra layer. So what happens if you did get like a chemical burn from touching a base? So the base, the first thing I would do is I figured out it's a base, is you touch that material and you'd realize it's gonna be like really slippery. Kind of feels like your skin just touched soap. Very similar to that concept. If you touch a base, what's gonna happen, and you didn't know it, if it's on your skin, it's going to eventually work its way through the two layers of your skin, the dermis, epidermis layer. As it works its way through the layers, it's going to start to eat away. It's going to start to turn red, pink, orange. It's eating away your skin, your live flesh. As it does it, it's going to obviously give you a sensation of pain, and it's going to be a chemical burn. How could you get rid of the chemical burn? You could neutralize it. If you neutralize it with maybe an acid, it would reduce the pain. You guys, hopefully you're not going to get a chemical burn in this class because we're not doing any labs. Problem with things in labs, a lot of the materials, the solutions you have in labs are going to be clear. So you think of clear, something clear is automatically water. If you make a sodium hydroxide solution, it's going to be clear. It's not water, it's sodium hydroxide. So another thing you have to know, whatever you're using in chemistry lab, maybe for cleaning at home, you should know what it is. You should know how it could affect your body. Maybe you're cleaning something. Don't mix chemicals together. Read the directions on the back. Figure out, is it safe to do this? What should I do? What are some precautions? Should I vent out the room? Should I run a fan in the room? You have one set of lungs. Take care of them. Last thing for notes here, Arrhenius acids. What should you know from this whole class for today? Arrhenius acid is going to be an H plus or hydronium ion. So please copy this down. H plus or H3O. Positive. H3O positive. We should know an acid is going to be hydronium. Hydronium ion. Acid. Hydronium. What should you know about Arrhenius base? Hydroxide. OH minus is hydroxide. Acids and bases. All right, that's it for notes for today. Once we're all set with this, don't turn off the notepad yet. Leave it open. We're going to use it to assist us with the examples. I do want to play another video on acids and bases. Back to the home page. Coke and Pepsi. Let's see what happens with a Coke can is mixed with a strong acid or a strong base.
What's being generated over there in the acid can, oh my word. We're going to show you something with aluminium today. And the thing is, we've got here Coke cans and Pepsi cans as well, so that it's fair. But when Neil gave them to me, I had a look inside, and you can see there, this one has quite clearly rusted. So these Coke cans are made of aluminium, whereas the Pepsi ones are steel. That's why we can only use the Coke cans to do this next experiment. So what we're going to do with these is to show a property of aluminium and how it reacts with both acid and with base. And that means it's a substance that's amphoteric. What we're going to do is we've got a solution of sodium hydroxide, that's our base, and we've got also hydrochloric acid, and then Neil's going to put the acid in and I'll put the base in at the same time, and we're going to see what happens to the aluminium cans. Yep. Go. Oh yeah, straight away you can see the bubbling there with the base. Clearly you've got a very vigorous reaction in both cases. So what's being generated here is sodium aluminate, and what's being generated over there in the acid can, oh my word, is aluminium chloride and water. We expected reaction with both, yeah, I hadn't anticipated to be quite so vigorous. I hadn't expected it to be quite so, wow! That is brilliant. So this is obviously a very vigorous, hot reaction. You've got a lot of fumes being given off, which is a good job why we did it in the fume cupboard. You can see all that smoke being drawn up into the extraction fan. I honestly thought the acid would have done more damage. Because when you think of acid, you always associate acids as being the evil guy of the chemical world. I think those Pepsi cans have gotten off very lightly. They may have had their tops cut off, but they've met a fate far better than the Coke cans here. Good old Pepsi for making them steel. Neil, can you clean that up for us? What's left is just the plastic around the outside of the can. All the metal's been converted to sodium aluminate. And that one's still going. The acid is still eating away at that can. And again, it's just leaving behind the plastic coating. It was a really exothermic reaction. And I didn't think I would actually see a can bubbling away like that. It's just incredible, isn't it? It looks pretty disgusting.
There you go. Some strong acids,
What's being
strong bases, and the effects of what they do. What they can do to a can. All right, what's next for class? Please open up the examples. We'll go through 6 examples, and I'll give you the rest of the time to work on the exit pass. So here we go. Examples, topic number 1, Arrhenius acids, Arrhenius base. You want the guided notes to assist us in this process. So here we go. All of this is referring to Arrhenius acids and bases. My guide notes. I'm going to take that last section of notes. That's all I really need. That last portion of notes right there. This right here. All right, question number 1. According to Arrhenius theory, a substance is classified as an acid will always yield what? These are legit Regents questions. What's the best answer for number 1? Throw in the chat. 21 people on right now. Arrhenius theory, a substance classified as an acid what makes an acid an acid? Acid for Arrhenius is going to be H plus ions. 1, H plus ions, hydronium ions. That is going to make an acid. Arrhenius acid, H plus, or hydronium. 1 is A. Next up, number 2. According to Arrhenius theory, the only negative ion in an aqueous solution of a base, negative ion base. Couple things to note. Negative ion base is what? Or what? Please record your answer in the chat. What's the best answer for number 2? Thank you. Thank you. 2 for 2. Negative ion base Arrhenius. Arrhenius theory. Thanks, JC. Please record your answer in the chat. Number 2, best answer. Quicker you guys give me some answers, the quicker you guys could work on the exit pass. The more time you'll have for the exit pass. What's the best answer for number 2? I have 3 responses. Thank you for those who did. I mean, which one makes the base here? Thanks, Eita. Yeah. A, OH negative. Thank you. OH negative makes the base. OH negative, base. Next up, number 3. Arrhenius base is placed in water. The only negative ion present in the solution is, please record the answer. 5 responses. Only negative ion present in the solution is what? One for 1, 2 for 2, 3 more responses. Thank you. So the O and the H have to be paired up together. It's going to be OH together, hydroxide together. Negative ion in the solution is going to be the O and the H. That polyatomic ion, hydroxide. 3 of the best answers is going to be choice A. 3 is A. Hydroxide, OH negative. There it is. Base, negative ion, automatically think Arrhenius base is going to be hydroxide, OH negative. Arrhenius acid is going to be either H plus or H3O plus, hydronium. 3 is A. Number 4, next up. According to Arrhenius theory, the acidic property of an aqueous solution is due to the excess of what? According to this theory, we're talking about acids. What makes an acid an acid? Put the answer in the chat, please. Thanks, Nalia. Oh, not Nalia. Nyla. Nyla, thank you. And you always answer to me, too. I always respond. Thanks, Nyla. Thanks, Lena. Thanks, Evan. Thanks. Over there. Easy. Choice B, acid. B is the best answer. Number 4. Nyla, I've been saying it really the whole time today. First time you got it, eh? Try better. If I'm messing up anybody else's name, please let me know. I'm sorry. All right, number 5. Next up, according to the Arrhenius theory, when a base is dissolved in water, it produces a solution containing only one kind of negative ion. What's the name of the negative ion for Arrhenius theory? Negative ion. Base. Negative ion. Choice. Thank you, guys. Hydroxide. Hydroxide is a base, negative ion. And last but not least, number 6. Which statement best describes the solution produced when an Arrhenius acid is dissolved in water? Wants to know Arrhenius acid. What is it? Please record your answer in the chat for number 6. Acid H plus. Only positive ion solution. There you go. Choice C is the best answer. Thank you very much. C is the best answer for number 6. The examples you can submit. You don't have to. That is done. Those questions are that easy. Figure out Arrhenius acid, Arrhenius base, plug it in. That's it. Last thing for today's class, going to the Google Classroom page one more time. Please open up the exit pass. There's 8 minutes left to class. I'm giving you the 8 minutes to complete this exit pass. There's 7 questions. They're very similar to the questions that we just did. Arrhenius acid, Arrhenius bases. Please complete this. This is going to be due tomorrow. I know it's not a ton of time. You have a minute per question. I'm putting you in a breakout room right now. If you have any questions, please feel free to ask for help. I'm here for you guys. Please join the breakout rooms. Please complete the exit pass right now. It is due tomorrow. If you have questions, please ask for help. Please complete it. Join the breakout room. Please complete it. If you get done early, we'll see you later. It's due tomorrow. All right, guys, once you're done, you're free to leave. If you have any questions, please let me know.
We ran out of cheese, right? American cheese.
Mhm. All right, guys, have a great day. Do not forget to complete the exit pass by tomorrow. You have 3 assignments due for tomorrow. Topic 5, electrolytic cells. Topic number 1, exit pass on Arrhenius acids, bases. And don't forget your guided notes are due as well. Have a great day. Enjoy this weekend. It's going to be really nice out there. We'll see you later, guys. Bye-bye. Bye, Matthew. Keep working hard. See you later. Bye, Todd. Bye, Ty. See you guys later.